Hello, everyone, and welcome to another episode of Algebra Fun Times. Today, we're going to be taking a look at something new. Specifically, we're going to be looking at 7.7 complex numbers. So, I'm going to take us on a little trip down memory lane to help us see where complex numbers come from. And hopefully, it'll be something that you personally can relate to. So, we've been taking a journey on solving. And as we've journeyed, we've also discovered some things about how we understand numbers. So, for instance, if we were to solve something like 2x plus 4 equals 10, that's supposed to be a 10, we'd subtract 4 from both sides, and we'd get 6, so that 2x equals 6, and we'd divide by 2, and we'd be like, oh, x is 3. Whee! Anyway, this is a whole number. Good times. Oh, no, I don't want to zoom. Sorry about that. Um, but often when we'd solve things like 2x, I don't know if I like this new program, minus 3 equals 10, we wouldn't necessarily get a whole number. Like if I add 3 to both sides, we'll get that 2x is 13. And then when I divide by 2, oh no, I have a fraction. So when this happens, we needed a new number set. We got a number that couldn't be reduced, and we called these, if you remember, the rational numbers, where rational meant ratio. There's still other things out there that we need to solve that might not have necessarily a rational solution. So say if you had something like x squared equals 4, we would go ahead and take the square root of both sides and get that x is plus or minus the square root of 4. But we know the square root of 4. It's 2. So I get two solutions off this, plus or minus 2. Now we did have other ways to solve this. We could subtract 4 from both sides and get that x squared minus 4 is 0, and then factor it. And then we'd use the zero factor property to say, hey, x is either 2 or x is negative 2. Now what's nice about all of these solutions, these are the same, but these came out whole as well. So this could happen from a square or anything with an exponent in it. We also saw ones with fractional solutions as well. Or sorry, rational solutions. I just mixed fraction and rational for some reason. But now we're going to look at something that's a little bit more complicated. What if I had x squared equals 5? Well, I could solve it like what I was doing up here and say, hey, I'll just take the square root of both sides. So I'll square root and I'll square root. But don't forget there's two solutions, plus or minus 5, plus or minus 5. So on this side, the square root of a square will just give you an x. Actually, I need to erase that plus or minus because it doesn't make sense. And then you're like, oh, well, I have a negative or a positive square root of 5. Uh-oh. That seems like something new. But it's not new, it's just strange, so to speak. These are the numbers you can't write as fractions. These are the numbers you can't write as fractions. Also known as the irrationals. In case you didn't notice, ir means not, so not the fraction guys from earlier. That's as good as it gets. We know other irrationals too, like pi and e and other stuff, dot, dot, dot. That's me being vague on purpose. They're out there, they exist. There's other things that are like this. Any decimals you have that continue on forever and have no pattern to them are irrational as well. And today we're going to be taking a look at not just specifically the irrationals, but the number set beyond the irrationals. So if you remember, these came up back when we were talking about number sets, when it came to like, okay, I want to be able to do all my operations like square and root stuff, but there's a problem. I might end up with some things where I end up with some roots I can't reduce, like the square root of 5 or the square root of 2. What we want to get into is, well, what if I have something worse than that? So this is what we're going to be up to today. We want to solve things like x squared plus 4 equals 0. So hopefully your natural inclination from everything we've just done is I should subtract 4 from both sides, get the x squared on one side by itself by doing so, equals -4. And from what we've seen so far, we don't know how to do this. Can't do the square root of a negative. Squares always come out positive. So it can't be done. Or at least we thought. As it turns out, there's a way to work around this. So just like before, whenever I needed something new, we came up with a new number set. I needed to be able to, not reduce into whole numbers when I divided. That's when the fractions came up, also known as the rationals. I need to be able to take things that were square roots and do them without actually getting a whole number result. Those were the irrationals. So it turns out they are always positive if you use real numbers. But we're not going to do that. Instead, we're going to use complex numbers. And this is where the complex numbers come from. Is to be able to solve this. That's the motivation behind it. So I'm going to define what complex numbers are for you so that you can understand what's going on here. So some things to talk about this to be careful with is that in particular, the word complex doesn't mean difficult. It's just they named it that. Just like real numbers doesn't mean that these numbers are fake. One of my favorite Senate hearings ever was when they were talking about complex analysis, which is just, doing analysis on the complex number system. And they said, oh, why are we spending so much money on complex analysis when we should be spending it on basic analysis, simple things so people can understand? And that to me just, says you don't understand what a complex number is, which is something you will know by the end of the day today. What is a complex number? Let's do ourselves a definition. So this is going to be two definitions, just so you know, sort of wrapped into one because they need each other. So we're going to define a new thing. Let I be so that when I square I get -1. Now don't think this is anything new. This is a lot like pi. It's a specific number that does something. Pi specifically is the ratio of circumference to the diameter of a circle for any circle. It's not anything special, just like e is the natural exponent that we will see later in the semester to do some financial math. And it's literally the last chapter we do, so that's coming up. They're not anything new. They're just specific numbers that do stuff and have special names. So I'm going to make a little note here. I is not real. In fact, many people call it the first complex number. And what it's going to do for you is allow you to square and get a negative. That's all it does and all it's for. So, what are the complex numbers? So we just defined what I is. That was our definition. A complex number is of the form. So this is just what they look like. So when you see form, that's what I mean. This is how they look. A plus bi. So I, we just defined what it is. So it's something that when I square it, I get -1. A and b are just going to be real numbers. That's it. So all this is doing is taking the real numbers and adding into it the one thing we need to be able to do the square roots of negative. So you might ask yourself, well, why I? Don't know the answer to that. I don't know why they picked I, but I can show you what it does. So if I have something like 2I and I square it, watch what happens. So one of the things you know is that, well, I behaves like a number, so I should just be able to distribute my square. Absolutely. So this would be 2 squared times I squared. That looks weird. Yeah, I'm definitely going with this program from now on. It erases so much better. So when I square 2, I'll get 4. And what do I get when I square I? I get -1. So this is -4. It's really designed so that when you square it, you get a negative. So hopefully you've seen that, oh, well, 2i is something that when I square it, I get -4. So 2i is a solution to our problem earlier, x squared equals -4, because it's something that when I square it, I get -4. So you might ask yourself, okay, I believe you on this one because I just seen it work. I squared it and I got -4. What if I wanted to do another solution to this? Is there one? Because what we've seen so far is that squares in general have two answers, right? When I square root 4, I get 2 and -2. When I did the square root of 5, I got +5 and -5. Let's see what the other one is. You might guess rather, poignantly that that doesn't look like words. Also, -2i works. So let's square that guy. I'm going to show you this works. Let's do green for fun. So I'm going to have to square -2 and square the I. Ooh, I used way more parentheses this time. So the square of -2 is -2 times -2, which is totally a +4. And then the square of I is -1. Oh, look, it's -4, because -1 times 4 is -4. So yep, here's the second solution. So one way you could summarize this is that, hey, I did find the solution to this. So 2i and -2i solve. When I take a square, I can get a negative. So when you think about this, it's just, what do I need to do? I make a new number system that makes this solvable. That's it. That's all there is to it. Nothing more. Now, one little fun note. Some people will define I to be the square root of -1. This is not incorrect. This is another way to think about it. So it's just a different way to think about I. And I'm going to use that idea as we go forward too. So I like to show you the pure original way it came about. It was when they were looking at solving things with squares in them, just so you can understand where this is coming from, but that's all. So the major way we are going to use this is to simplify roots. So use to simplify roots of negative. Excuse me. Negative numbers. Woohoo! Let's do some examples with that, because that's what we're up to right now. Oh no, I'm at the bottom. I'm going to need a new page. Okay, I'm going to pause this because I do not remember how to get a new page. Oh no, it lets me go. I don't know why it was locked up like that. That was weird. Okay, let's do some examples. So we're going to simplify the root as much as possible. All right, so our first one is we're going to do the square root of -81. Okay. So I need something that when I square it, I get 81. So I'm going to think of this as -1 times 81. Yeah? And remember, one of the things we know, and this is what I'm going to be using, that if I do the square root of something squared, I will get it back. So I'm going to use that a bunch. just so you know. Okay, so square root of 81. Oh, I need something when I square it, I get 81. So that's going to be 9 squared. And over here, I've got I squared because it's something that when I square it, I get -1. So I'm going to think of this as the square root of 9 times I squared. So I'm just combining them under the same square. So this is really 9I. Now I did that the long way, for sure. There's definitely shorter ways to do this. Why did I zoom out again? That was weird. When I look back at this, it's not going to make any sense because it'll be like zoomed out, zoomed out, zoomed out. Sorry. Let's do the square root of -13. So I'm going to use the same idea for this one. So negative, okay, weird. Sometimes it picks up my pen when I just move it. So -1 times 13. Now 13 is not a perfect square, so I'm not going to be able to do anything with that. Crap. I mean, oh no. So I'm going to rewrite this as, well, you know, I squared times 13. And the only thing I'm going to be able to do is the square root of the square. So I'm going to, you know, think of this as, well, negative the square root, not negative. So I'm going to have to only be able to simplify this portion. So I'm going to do the square root of I squared times the square root of 13. And, well, the square root of square will just give me I. So I get I square root of 13. Now when we write I, we usually write it second, so backwards. So usually I'll write 13 and then I. And it's important here that you're clear that, like, I is not under the square root. So be careful with that. Just so you know. Let's do one more with simplifying, but call it, you know, the right letter for fun. I do that constantly. Let's do the square root of -90. So this one's a little harder. So I'm going to break it up into pieces. So I've got my -1. I'm going to think of this as -1 times 9 times 10. So I've got 3 parts, some of which are perfect squares, some of which are not. So I'm going to rewrite this as the square root of I squared, 3 squared, because that's 9, and then 10. And now I'm going to split my square root into pieces. So I get the square root of I squared times the square root of 3 squared times the square root of 10. So hopefully square root of squares, you know what's going on. That's going to be an I, a 3, and a square root of 10. And then just like you've seen before, I tend to write this the same way your book does. So I'm going to have the I at the end and the square root of 10, the number in front. Now, some other reasons why I'm writing it like that is because you hopefully remember that, you know, complex numbers look like A plus B, I. It's number times I, so number times I. So in particular for this one, if we were thinking about it in terms of complex, B would be 3 square roots of 10, and you're like, but there's no plus happening. You're right, because A is 0 for this one. Good times. Let's look at some more operations with I. So we're going to look at how to combine some I stuff and do some multiplying. So I'm going to do just some operations with I. So I'm going to be doing some adding, subtracting, multiplying, and dividing. Well, not dividing. I'm going to save that for another example. We'll just do the simple stuff. So hopefully you remember this kind of stuff. Perform the operation. I missed the F. And the O. And the R. It always sounds so, like, medicinal. Perform the operation. What am I doing? I'm going to add. So I'm going to take 3 plus 4i, and I'm going to add to it 4 minus 7i. Gotta make my eyes more big so they're noticeable. Okay. Whew. Just like you may suspect, how do we add? Well, we add like terms. So when are things like? When they have the same variables or numbers to the same exponent. So things that are like will be, well, the things without I on them. That was not the color I meant to do because these do not match at all. There we go, green and green. And the things that have I with them. Ta-da! Okay, so I'm going to rewrite this as grouping my like things together, 3 plus 4 plus 4 minus 7i. Wow, that 7's wild looking. I have to pause because I need to sneeze. Allergy season is not a fun season, so I'm adding my like terms together, my stuff without eyes, and then my stuff with eyes. Cool. And don't drop your negative. So I get 7, because that's 3 plus 4, plus 4 minus 7 will give me a negative 3i. Now I like to write my negatives like this. If you don't, you could totally write this as 7 minus 3i, which is a little simpler, a little bit, less long. That's the word I want. Let's do another one. So for this one, I'm going to write it out. I want you to anticipate what you think is going to happen for this. So I got 1 plus I minus 3 plus 4i. So I'm subtracting this time. So I hope you're not surprised when I go ahead and just distribute my negative. So boop, boop. Minus 3 minus 4i. So just like before, I'm going to combine my like terms with if you remember the fun symbol stuff. So 1 plus, not plus 3, minus 3. Almost made a boo-boo. Will give me a negative 2. And then I lose 4 more i's, I should have negative 3 i's. Beautimus. Hopefully that was pretty simple for you. And you're seeing that operations with the complex numbers isn't all that complicated. See? The name doesn't make a whole lot of sense. If I could go back in time, I would tell them, hey, rename this because, let's rethink this through. These students are going to be confused by this because you're doing the things. Anyway, so you're going to have to be careful here. This is a very traditional way to write this. I'm going to take the 4i and distribute it in and multiply it. So as I do that for my first term, I'm going to get 4i times 4. In my next term, I'm going to get negative 6i times 4i. So I'm going to do some rearranging here so that my numbers that I can combine are next to each other. So I'm going to put 4 times 4 and then an I. And over here I'm going to do 6 times 4 and then, well, I times I, which you hopefully recognize to be I squared. Okay, 4 times 4, totally a 16, minus 4 times 6, which will totally just give me a 24. Oh, I dropped an I, gotta be careful. Everybody should have I's. And then I squared. And then you remember, oh, teacher, but I squared, that's negative 1. So here I have a negative 24 times 1, which will give me a 16i plus 24. Now this is written improperly because my I term is first, my 24 is second. Remember, pro tip, complex numbers, A plus BI form. That means I got to put the stuff without the i's first, and then the stuff with the i's second. So this is the proper form for your answer. I'm hoping you've been noticing that I've been doing that from the very beginning. Let's do another one. Remember, if I'm going too slow, you can always slow down the video on YouTube. You can speed it up. You can pause. You can go back. I forgot what letter I'm on. Like always, I'm on D. That D is beautimus. All right. Just when you thought it was safe to go back to complexing, let's go ahead and do some multiplying. So this shouldn't be a shocker. Hopefully you look at this and think, oh, I've got something with 2 terms, a binomial, times something with 2 terms. I can FOIL that. Yay! FOIL to the rescue. Hopefully this brings back fond memories of foiling. So I got to do my firsts. That'll be 3 times 5. My outers, I always screw this up and do my I before my O. My outers, which will be 3 times negative 3i. I was just overusing parentheses on this so that you don't have as many mistakes. My inners, which would be, let's do 5 times 2i. I like to write the stuff without the i's first. Just makes it look nicer. And then, let's see, plus 2i times negative 3i. Okay, be careful with your signs. There's lots of negatives floating around. We're going to do this very carefully and slowly so that we don't miss anything. Oops, times. I put those kind of far apart. That was weird. So 3 times 5 will just give me a 15. I got to be careful here. I have a negative, so this is going to be negative overall, so I'm not going to write plus, I'm going to write minus. I have 3 times 3, which will give me a 9, and then an I. Here, I'm going to have a 5 times 2i, which will be 5 times 2 is 10. I. So I'm going to be able to combine these in a minute, and I want to see what this last one does. So I have 2 times -3, which will give me a -6, and I times I, which will give me an I squared. Ooh, so hopefully remember what that does from what we saw earlier. Oh, no, I zoomed in again. I need to quit doing that. I think it's going to scroll, and it's not. All right, so I've got a 15. I'm going to combine my two i's together. I have -9 of them and then 10, so that's really just one I. And then -6 times a -1 because I squared is -1. So instead of -6, it's going to be +6. And then I'll add my 15 and my 6 together. So that'll give me 21 plus I. Is that what you saw coming out of this? Hopefully so. Now these are ones that like I have to multiply them out almost every time because I almost certainly will miss something if I try to guess what I think it's going to be. But there are certain ones that when you guess, so to speak, things go well. Let's take a look at some. What am I on? E? Yeah, E. Let's do 2 plus 3i. That I is not, well, hopefully that goes better. And then 2 minus 3i. So let's go ahead and FOIL this out. Now this one I'm going to do twice just to kind of prepare yourselves so you can see what happens. So first up, let's FOIL away my lovely mathematical minions. FOIL to the rescue. So firsts, which will be 2 times 2 plus, or maybe minus, I don't know yet, I'm not going to fill it in. My outer 2 times -3. Okay. I. Inners, so plus 2 times 3i. And then last, so negative, and then we'll do 3i, oops, times 3i. Cool. Let's multiply to our heart's delight. So 2 times 2 will give you a 4. 2 times 3 will give you a 6i. Don't forget that negative. 3 times 2 will give you a plus 6i. Oh, I'm hoping you notice your oi appears to be nothing. Those are going to add and make nothing. Minus, now I have 3 times 3 to make 9. And then an I squared. And hopefully you remember what that does. So I'm going to get a 4, and then 6i and minus 6i, those are going to make nothing. So I'm going to write the 0 this time for fun. 9, and then I squared is -1. So this is like a -9. So here I get 4 minus 9, which is just a 5. Whoa. It's real, man. And this is something that's kind of like special. That's a weird symbol. It's like really special about the complex numbers. You can multiply two complex numbers together and get a real number, specifically when they look like this. Hopefully you look back at this and you're like, I think I've seen this before. Isn't this the difference of squares? You are 100% right. So I'm going to write this a slightly different way and do it a second time, which I warned you about when I started this problem, but you know what? That's okay. We're going to do it again. So if you were like looking at this and being like, oh, isn't this just a plus b and a minus b, which I know to just be a squared plus b squared? That b looks weird. Yep. So here a is playing the role of 2 and b is playing the role of 3i. And I'm going to scroll this up because it's just barely going to fit. But remember, the answer we expect to get is 5, right? If this works. So a is 3, or sorry, a is 2. So I should get 2 squared plus just 3i squared. Now watch what happens. 2 squared is 4. And then plus 3i, and I'm going to square both of them. So I'm going to square the 3, get a 9. Square the i and get a -1. So this comes out 4 minus 9. Oh my gosh, it's -5. Wow. Okay, so I want you to recognize this because we're going to see that, hey, as it looks out onto this, you can take complex numbers and combine them in ways that will end up being real numbers. So there's one thing I want you to note from this is that all real numbers can be written as complex. I need to scroll up. And here's how you do that. So if I have a real number like, I don't know, 7, I just write it as 7 plus 0 times I, because it's got no I part to it. Not all complex numbers are real. So like I said, it just adds something a little extra to this that allows you to solve some things. So for instance, like the number, 7 is both real and complex. Here's how I write it as a complex number. However, things like 7I cannot, it won't let me write that C. Cannot be written as a real number. In math, we like two-way streets, like things that have opposites and can go two different directions and always work. But in some places, that just simply doesn't happen. And here's one of them. Well, it's interesting for the fact that it only goes one way. I can take all complex. I can take all reals and write them as complex, but not every complex number can be written as a real number. Okay, let's do one more example with this stuff. So I believe I am on if square root of a negative times the square root of a negative. So here's where you have to be super uber careful. Your temptation might be to combine these two, but you absolutely shouldn't. So we're going to rewrite this. So instead of square root of a negative, I'm going to think of this as the square root of negative 1 times 3 times the square root of negative 1 times 4. We remember the square root of negative 1 is I, so here I'm going to get I square roots of 3 times I square roots of 4. Hopefully you know the square root of 4 is 2. And now I'm just going to rearrange some things. I'm going to group my numbers together, 2 square roots of 3, and then group my i's together, so I end up with I times I, which is I squared. Hopefully you remember that I squared is negative 1. So this comes out negative 2 square roots of 3. And that's it. Now, this is a little strange because it looks like negative times negative makes a negative. Yeah, complex rolls like that. It's a little strange. Yeah. And what you have to be careful about with this is that a lot of the times people will do this by just like, oh, can't I just combine these two roots? I'll do the square root of negative 3 times negative 4, which will give you the square root of negative 12, which if you do, well, positive 12, sorry. Negative times negative makes positive. And then you notice these aren't the same. This is the wrong way to do this. You have to be careful. If it's a negative under the root, you need to write it in I notation first. So I wrote this all in red on purpose. Warning. Anytime you have square root of a negative number, always rewrite it as I times the square root of that number first. And it'll prevent you from making this mistake, where you would do this bad thing. Bad. Good. I don't know. Hopefully that sticks in your brain. Always rewrite it in I notation first. If it's negative root, make it complex. Every time. Let's look at the other use of this. So the last thing I want to do is I want to divide. Oops, that was supposed to be example. Oop. Divide by simplifying the denominator. Okay, so we're going to be looking at two things with this. Well, not really two things. Something kind of simple. So the problem with this is I have this difficulty of I have a complex number in the denominator. Oh, that's going to be difficult. I should probably deal with that somehow. You are right. So how you deal with this is you're going to multiply by something that'll make this be a perfect square. So in this one, you can pick either 2i or negative 2i. I'm going to pick 2i. What I want to do is I want to make it so that when I multiply through, I end up with an I squared, and therefore it'll go away. So my choice here was just so that I end up with something that gets rid of this I in the denominator. So for the upper one, I'm just going to distribute. So I'll end up with a 4 times 2i plus a 3i times 2i. And in the denumerator, I'm going to end up with a 2i, well, squared because it's 2i times 2i. And I'm doing that on purpose because I want that I to go away. So for that first term, 4 times 2 will give me 8i, plus 3 times 2 will give me a 6i squared, all over. Now in the denominator, I'm up with 2 squared, which is 4, and I squared. And be careful, don't simplify yet. Things are going to get better, I promise. Okay, so for my numerator, 8i isn't going to get any different, but 6 times I squared, hopefully you remember I squared is negative 1. I'm going to have to fix that. And in the denominator, I'll get 4 times negative 1 as well, because I have an I squared. So I'm going to rearrange this. So 6 times 1 will give me a negative 6. I'm writing this as an a plus bi form, all over negative 4. So then I'm going to use separation of the numerator to simplify this at last. So I'm going to end up with 6 over negative 4 plus 8 over negative 4i. And you want to do this because remember, we always want to be in a plus bi form. So I'm trying to come up with a number here times I, real numbers. So 6 divided by 4, negative divided by negative, that'll be positive, so I can reduce this to 3/2. And then 8 divided by negative 4 will give me negative 2 times I. So looking at this, I'm finally in a plus bi form, which means my a is 3 over 2, my b is negative 2, and my I is in the correct position. So as you look at this, you're going to multiply so that you can take this and turn it into a plus bi form. This is really your goal when you run into these problems. Let me show you how this can get a little complicated. Now, it becomes a little bit more difficult when you have a denominator that's binomial. So I'm going to teach you strategy here. So if it's a binomial, we're going to multiply so that we have a difference of squares. Because that will always be real. So for this one, I'm going to multiply by, I want to have 2, and it's got a minus in the middle, so I need the plus version. We're going to do a couple of these so you can get a feel for how this looks. And then I'm going to FOIL to my heart's delight. This is going to be a little bit of a mess. So in the denominator, I know what I'm going to get. I'm going to get a squared minus b squared. So I'm going to get a 2 squared minus a 3i squared. That one's easy. I picked my multiplication so it would do that. So this denominator ends up being real. Actually, I'm going to do the denominator so you can see it comes out real. So 2 squared is going to be 4 minus 3 squared will be 9, and I squared will be negative 1. So keep on doing the denominator. I'm going to do the numerator in a minute. Calm down. 9 times negative 1, or negative 9 times negative 1 will give me a positive 9. Okay, I'm going to have to do the numerator now. Hopefully at this point you see you're going to get a 13 and it's not too bad. All right, let's do our foiling here. So I got to do my firsts. So 2 times 1. My outer, 1 times 3i. My inner, 2 times I. That one's easy. Plus 3i times I. That's kind of pretty. Cool beans. Okay, let's see how this goes. So I'll do 2 times 1 and get 2. 3 times 1 and get 3, so I'll have a 3i, and that's just a plus 2i. And then plus 3i squared. Cool. So looking at this, I'll have a 2 plus, and I can combine my i's together, so 3i plus 2i will give me 5i. And then remind myself that I squared is negative 1. Oh, see, I still needed more steps anyway. These are longer problems. Okay, so in the numerator I have 2 plus 5i minus 3 all over, well, we just already established 3 plus 9 is 13. That's pretty. So now I just got to combine my 2 with my negative 3 to get negative 1 plus 5i all over 13. This is not going to be pretty. Let's split our numerator. Negative 1 over 13 plus 5 over 13i. So there's our beautiful complex number we get off that first one. Ew. Let's do another one. So as I write this one, I want you to be thinking to yourself, what should I multiply by to make that denominator go away? Hope you're ready. Let's not do 3. I have too many 3's in this lesson. Let's do a 1. So think to yourself, what should I multiply by to make that denominator be real? Oops. Not equals. Hopefully you picked 1 minus 4i, because it's just the same thing as the denominator with the sign change. 1 minus 4i. So if you don't trust me on the whole a minus b thing, I'm going to go ahead and multiply this one the hard way so you can see that it does come out the same. So let's just foil away, people, even though it's really unnecessary, but it's kind of nice to see. So I got to do my firsts, which will be 2 times 1, my outer next. 2 times a negative 4i, I wrote that poorly, but oh well, plus inner I times 1, which is just I, and then my lasts, so minus 4i times I. I don't like it when my eyes start to look so small you can't tell what they are. Alright, denumerator time. Let's do the denominator. 1 times 1, my firsts, my outer, 1 times negative 4i, I did it again, my inner plus 1 times 4i, and then my lasts, 4i times negative 4i. Ooh, just barely getting it in there. Okay, let's fix this up so that I can hopefully make it fit better. So 2 times 2 will give me 1, negative 4 times 2 will give me negative 8i for this one, plus an I that I already did, minus 4i squared, already looking better for that denominator. Why did I do that? I have no idea if that one's going to be shorter. Alright, 1 times 1, totally a 1. 1 times negative 4i, negative 4i. 1 times positive 4i, positive 4i. There's the inner part going away, just like I promised it would. Negative 4 times negative 4 will give me negative 16. An I times I will give me an I squared. Let's handle some combining, and then we'll take care of the I squares in this next one. So my 2 and my 1 are just going to hang out for a minute. Hopefully they'll turn into something. On the numerator I have negative 8i plus an I, so I'm going to end up with negative 7i. And the denominator I have negative 4i plus a 4i, so those two are just going to add to nothing, so I'm not going to write it. Numerator, so plus 0. Yeah, there we go, just to keep track of stuff. Minus 16i squared is negative 1. Minus 4i squared is, well, negative 1. Woohoo! Okay, almost there. I believe in us. So in the top, I'll have a negative 4 times negative 1. So that'll give me a plus 4. And make those i's big enough. On the denominator, I'll have 1 plus 0, which is 1. Negative 16 times 1 will give me a positive 16. Oh boy. So that's going to give me a really beautiful 17 in the denominator. I keep calling it a weird name. It looks like a seahorse. Okay, I have 2 plus 4 is 6 minus 7i. And now I can split that numerator. So I have 6 over 17 plus, not plus, minus 17, sorry, 7 over 17i. So this is my A and this is my B. Woohoo! Okay. Oh no, what happened there? Let's undo that. That was weird. Okay. Let's do our last examples of the day. Let's look at how to simplify large powers of I. Here we go. Yep. I like the undo button. Example. And this takes some trickery, just so you know. Why did I write simplifying when I want simplify? I was able to get the eraser to work previously. Here we go. Kind of working? Not really. It's trying to lasso it. That's what it's doing. It's not erasing. It's doing the other thing. Cool. What do I mean by large powers of I? Well, let's just start out kind of simple. Let's do I to the 7th power. So keep in mind in your toolkit, no, you know that if I have just one power of I, that's the square root of -1. And if I have I squared, that's going to be -1. So my goal is to write this as much like -1 as I can, because I know how to deal with -1. So I'm going to think of this as I to the 6th plus 1. And hope you remember that when I have addition in the exponent, that's the same as multiplication outside of the exponent. So I have I to the 1st, and then I'm going to deal with the I to the 6th power. So I to the 6th, I'm going to think of as I to the 2 times 3 times I to the 1st. Don't worry, I to the 1st I'm just going to change into the square root of -1 in a minute. So power times power is the same as power to the power. And then, screw it, let's just write it now. All right, here we go. Ready? I squared, -1, cubed. Why did I do that? Let's just leave it as I. That's shorter. Oops. There we go. I. Okay, -1 times -1 times -1. -1. This is just -I. How do you like them apples? Okay. Well, let's investigate further. Let's try a little bit of a more interesting one. Let's do I to the 21st power, because you totally saw that one coming. So how am I going to do this one? I'm going to rewrite 21. I'm going to try to do the same thing. I'm going to pull out as much evenness as I can, because I know that when I look at an even power of I, I'm going to get a bunch of -1s. So I'm going to think of this as I to the 20 plus 1, pull off an I, and then, so this is going to be I squared to the 10th power, because that'll give me 2 times 10, which will give me 20, times I. You remember that I squared is -1, times I. Why did I put parentheses around that I? I don't need it. Don't need it. I do need more space. Okay, -1 to the 10th power, that's -1 times itself 10 times. That's an even number of times. Anytime you do negative times negative, so it's an even number of negatives, you get a positive. So this is just going to be +1 times your I, which will just give you an I. Woohoo! Okay, hopefully you've got the idea of what to do when they're an odd exponent. Let's try one that's even. Let's do I to the 30th power for fun. Come on. There we go. So I'm going to rewrite this as I squared to the 15th power, because 15 times 2 will give me 30. I squared is -1. -1 to the 15th power, that's going to be -1 times itself 15 times, which is -1. Done. Yep. Convince yourself this is true. If not, we might need to talk. Okay. Last one, and then I'm going to talk to you a little bit about what just happened here. Let's do I to the 40th. I already did 20, didn't I? I don't know if I did 20. Let's do 40. Alright, so I'm going to think of this as I squared to the 20th. That's why I was saying 20. Already thinking ahead. I squared is -1, 20th power. So I have an even number of -1s multiplying to each other. That's going to be a +1. So I'm hoping what you've seen from this is the different possibilities. So when I take I to any power, it's either going to be one of the following: negative I, 1, or negative 1. And it's this reduction that allows you to easily work with complex numbers. This is why the structure of I is really, really cool. Sometimes it comes out real, sometimes it comes out complex. It's all a matter of what's happening, man, and how they multiply. So hopefully you think about this as you're working through your homework this week. The one thing I would be cautionary about you with this is if you do I to a power and you don't get one of these four, you have messed up somewhere. So it's just a nice little thing to know about I, so that when you're working with it, you don't have anything crazy happen, you know? But that's about it. Okay, hope you enjoyed this video. I will see you next time.